Okay, Jaroslav, I will start by introducing you.
Okay.
Welcome everyone to the WST 20 minutes time domain working group seminar series after the summer break. Today we are very pleased to host Dr. Jaroslav Merc, a postdoctoral fellow at the Istituto de Astrofisica de Canaria in Tenerife and at Charles University in Prague. His research focuses on long-period interacting binaries, especially symbiotic stars, using multi-wavelength observations and survey data to investigate their variability and physical processes. His presentation today is entitled Optical Spectroscopy of Symbiotic Binaries from Discovery to Diagnostic. Please join me in welcoming Dr. Jaroslav Merc. Jaroslav, thank you for being with us today, and the floor is yours.
Thank you very much, and thank you for the invitation to give this seminar talk. So I will speak mainly on the optical spectroscopy because that's a facility that we are planning of symbiotic binaries because that's my favorite target. These are my favorite targets, and I will try to guide you through the ways how we use optical spectroscopy in characterizing and even discovering symbiotic binaries. So first of all, I think that not everyone is super familiar with symbiotic binaries because that's a small family of binaries actually. So this is the take-home message about symbiotic binaries, what they are. It's important that these are strongly interacting binaries where you have a donor, which is a red giant, so an evolved star of a K or M type spectral type. And then the accretor is a white dwarf or a neutron star, so the star at the end of the very end of the evolution. But given that we have a red giant donor, the mass is not always transferred only through Rauschlob overflow, but it can be also transferred through, via wind, and that means that you have a lot of material which is in the vicinity. So you have a nebula which is photoionized by the hot companion. So you see the nebular emission, and in some cases you see dust, which is more prominent in near infrared. And also very important is to remember that these systems are very wide. So they belong to the widest interacting binaries because the orbital periods are from hundreds of days typically, but it can go up to decades. So these are kind of cousins of cataclysmic variables, which are maybe a bit more well known. But I don't like to put them in the same family, like a subgroup of cataclysmic variables, because cataclysmic variables typically have orbital periods of hours. So we are much wider with symbiotic binaries. As always, everyone is introducing their own objects as being the most important in the astrophysics. So symbiotics are also very interesting and important for understanding a lot of astrophysical processes from mass transfer and accretion, jets, winds, dust formation, thermonuclear outbursts, enrichment of the interstellar matter, but also they're an important piece of stellar and binary evolution because these objects interact, and that's something we still don't fully understand in the models. Kind of, they were also suggested to be supernova 1A progenitors. They were also it's claimed that they are very important for explaining the magnetism among white dwarf binaries, and also with the future gravitational wave observations. These are progenitors of closed double white dwarf binaries, which will create a gravitational wave background or foreground or what do you want. So their understanding is like they are quite interesting for many aspects of astrophysics. They are very complex, and I like to show our Aquarii, which is one of the closest symbiotic stars to us, as an example, because in this particular case, it's so close that we can actually resolve the environment around the binary. And you see from the image from HST that this is very complex collection of jets and previous outbursts, and the binary itself is actually somewhere there in the middle. And it was this is one of the very few examples when it was resolved by actually planet hunting instrument on VLT sphere. So you see here in this case that this is the very middle part, which is on the right, where you see the both components of the symbiotic binary. But actually most of that complex structure is from the former outbursts and jets and so on. And it is a time domain problem because this one is close. So it was observed several times in past, and you actually can see this is evolution. It's 9 years of evolution, and you actually can see in real time kind of that this object is changing, it's evolving. It's one of a very few examples where we can see that in this way, right? Because this one is close, all the other look like just dots on the sky. So you need to get some other type of data to really see what is going on. And of course, optical spectra are one of the most important ingredients. Here is a kind of a zoo of symbiotic spectra. So these are the well-behaving symbiotic stars. You see the hottest K-type donors on the top, and then going down, it's a cooler and cooler donor of M-type at the bottom. But what make them kind of conspicuous, and also this is the way how they were discovered in past, is not only that you see the cool star, the molecular bands, which means that you have a very cool star of a few thousand kelvins, but you see strong emission lines, and strong emission lines of hydrogen, helium, but also of highly ionized species like iron 6 or iron 7, oxygen 6, and so on, which the star itself, the cool star itself, cannot produce. So you need something else, some other ingredient, which is the hot companion that is actually photoionizing the nebula. And this is just a subset of stars. This we call stellar type symbiotic stars, S-types, because you actually see the stellar photosphere. If you have a lot of dust, an evolved Myra donor, then you don't see the cool companion in optical, and actually their spectra, as you can see here, look like planetary nebulae. So you don't have any continuum, just a bunch of very prominent emission lines, and you really then need to have some information from other spectral wavelengths, for example, from infrared, to be sure that what you see is actually a symbiotic star. And the complication in this zoo of symbiotic stars are those that actually look like single giants or almost like single giants because they don't have such luminous hot companions. So this we call accreting only, in contrast to shell burning, where you have a shell burning in the shell of the white dwarf, which is producing the high luminosity. And those are very hard to classify just based on the optical spectra themselves, because the only hint is maybe faint emission lines or some UV excess, but still they mostly remind just the single giants. So these are the hardest to find in optical ranges. Then if you have X-ray information, then it can help. And also this, what I showed you, is again just a kind of static spectra, but symbiotic stars are variable. And therefore, this time domain aspect of WST, for example, is very important because they are changing a lot in time. And these are light curves, so these are not spectra. These are light curves over 30 years of selected symbiotic stars, and you actually see that there is a lot of things going on. There is some variability which is related to orbital motion. For example, in the yellow one are Pavonis, you see the eclipses. But also in the top one, AG Pegasi, there is some kind of sinusoidal variability in the quiescence at the very beginning, but then there is a lot of outburst activity going on. And all this activity is also connected with changes in spectra. So for example, here, you see in blue, it's a quiescent spectrum. In red, this is outburst spectrum of the same star. And you see that the molecular bands are less prominent just because we have more flux from the outbursting component, which is the white dwarf. But also the highly ionized emission lines, which are marked by blue arrows, are missing in the spectrum because the cool component is cooler. The hot component is cooler at that point. So the lower ionization pops up, but the high ionization lines disappears. And some are even accompanied by the outflows of matter, as you see in the panel where you see the P Cygni profile. And some are more drastic, the outburst, especially symbiotic novae, which here is shown RS of Yuhi, one of those recurrent novae. So actually you see in the light curve, in the recent 20 years, you see two outbursts in 2006 and 2021. And then on the bottom panel, that's spectroscopic evolution. And you see how very fast the evolution is. In contrast to classical novae, given that you have a lot of material around the system, then the ejecta from the nova outburst is actually colliding with the surrounding material. So you see the deceleration, and therefore the lines are getting thinner and thinner. And with connection to that, there is a lot of physics that you actually cannot get from the light curve itself. So you really need the spectroscopic spectroscopic observations. And one of the open questions in this is related to T Corona Borealis, the star we are all waiting for the outburst to happen, hopefully soon. And here are the light curves from two last outbursts of this star. And what you actually can see is that after the main outburst, this main nova outburst, there was some rebrightening, let's say, the secondary outbursts or how to call that, the maximum, but we don't know what that is. There is a theory that it could have been irradiation of the red giant by the cooling hot companion, as proposed by Munari, for example. But we really need spectroscopic observation to be sure. And the outburst should happen soon. So here we really need this spectroscopic ingredient, because with photometry alone, we cannot be sure about the physics behind this. There are also spectroscopic changes related not to the outburst evolution itself. Here you see the Mira pulsation of one of the symbiotic stars, and on the bottom panel, then you see how the spectrum in minimum look like in comparison with the maximum. And the changes here are mainly because the cool companion in maximum is so bright that it's actually hiding the symbiotic symbiotic nature of the star. So you really can see that only in the minimum. So if you have just a single snapshot observations of some stars, you can actually misclassify them, because MIRAS itself can show emission lines due to the shock in the atmosphere, but not of the high ionization. But in the upper spectrum, in the red one, which is in the maximum, you actually cannot see any highly ionized emission lines. So you really need to get these observations in the minimum of the Mira evolution. But anyway, for most of what I showed, the spectroscopic changes are kind of also observable in photometry, in that sense that you can pick up that something is going on with that star, because there are changes in brightness, but not every time. And this is actually, I think, what when I was showing this on the WST spectroscopic alerts subgroup, catch the attention, because this is my recent paper on one of the symbiotic stars where we detected the outflows, as you see in the P Cygni profiles. And what is interesting about this is that that's something what you actually cannot see from photometry, that it happened, because you see the outburst, what is in this panel here. So you see the brightening, but all these three spectra were actually taken in the maximum. So the fact that the outflow happened, and actually since then it's already gone. I have some other observations, and it's not there anymore. So this all happened within a few months time scale, but there is no hint of that in photometric observation. So you really need the spectroscopic monitoring to see that something like that happened, and to understand then the physics behind the outburst. And this additional component, which is the spectroscopy, is without that you just cannot know. While you know that the outburst happened. So this is something really for which the alerts, actually spectroscopic alerts, would be essential for this kind of physics. And the other, that's actually the first part of the title, from discovery. So yes, for diagnostics, as the second part of the title of my talk, the spectroscopy is essential, but it's also for discovery. And there is a lot of space here, just because I just listed some of the estimates of the size of the symbiotic populations in the galaxy, and it ranges from thousands to hundreds thousands. Okay, I think that the hundreds thousands are a bit overestimated, but anyway, still, even the lowest numbers are higher than the currently known number of symbiotic stars. So there is a huge potential in discovering new symbiotic stars. And there are many ways how people select the candidates. And I just listed few. The very popular way is to use the narrowband photometry to select H-alpha emitters, kind of red H-alpha emitters. But then the follow-up by spectroscopy crucial really to be sure that you are selecting the symbiotic stars for because without that you just cannot confirm. And it's the same with other ways how people tried with the multi-wavelength photometry kind of approach. So you are searching for UV excess, or with Gaia DR3 data. When you are using even the low resolution spectroscopy to pick up candidate, then you need to have a spectroscopic follow-up. Okay, if you are picking candidates from spectroscopic surveys, that's kind of by definition you already have spectroscopy in advance. So there are very few efforts also like that. Because the main problem is that you have a lot of contaminants, so objects that in some parameters can look like the symbiotic stars, even if you just pick up the candidates from narrowband photometry, but also you have some additional data. This includes planetary nebulae, young stellar objects, B stars if they are reddened, cataclysmic variables, even pulsating stars, MIRAs, as I said, can have emission. So you can end up with a lot of contamination in the samples. And just as an example, these are spectra. Two of them are planetary nebulae, the orange and the red one, and one in the middle is a symbiotic star. And actually, you see that they look very similar. So if you look closely, that you see that there are some highly ionized emission lines which are present only in the symbiotic star and not in the PN, but there are some dense young planetary nebulae that actually can look very similar. So then with the spectrum like that, you can analyze the densities and so on. So you can get your answer if this is a symbiotic star or not. But if you are starting, for example, with Gaia BPRP spectroscopy, which is now quite popular to use the Gaia data, then without additional follow-up, you cannot tell. So again, here, the two in blue are symbiotic stars. These are especially these dusty symbiotic stars where you don't see the strong continuum in optical. And the rest are planetary nebulae, and you clearly see here that basically their low resolution, very low resolution spectra look exactly the same. And then it's not the problem of the dusty ones only, because the S-type symbiotic stars, those that have the stellar continuum, can look, especially if you have just a limited information, so narrowband photometry, can look like T Tauri stars. And here in orange, it's T Tauri itself, and you see that basically the shape of the continuum and some of the emission lines are exactly the same. And again, if you are in very low resolution, then you just cannot distinguish between those. So you really need to do high resolution follow-up, spectroscopic follow-up, and include some additional information for T Tauri stars. For example, it's astrometry is also helpful because it positions symbiotics somewhere else in the color magnitude diagram than T Tauri stars, for example. Just an example of other possible contaminants, as I said, the reddened BE stars, for example, on the left panel. If you use the narrowband photometry, these will be picked up as H-alpha emitters, and they will appear red because they are reddened. So their shape of the continuum, especially that the bottom one, is exactly what I showed you. So then you really need a spectroscopic follow-up, because without that, you cannot classify those objects as symbiotics, otherwise you are introducing a super huge contamination. And the example of a few pulsating stars, MIRAs, is on the right, and again you see that it can be actually very similar to what you are looking for, so you need spectroscopic follow-up. The other thing is that if you start with low resolution or narrowband photometry, for example, then you can miss a huge population of symbiotic stars just because you need to set a threshold for your H-alpha emitters relatively high. Otherwise, you will be finding a lot of just late type stars, because it actually seems that there is kind of excess in emission at the part where H-alpha is, just because on the other, the both sides you have molecular bands. So those will appear as a faint emitters if you just do some criterion on a photometry. just because of the molecular bands. So then you need to set your threshold high, but then you miss actually a large population of symbiotic stars. For example, here you have CH Cygni and Y Geminorum, which are both known symbiotic stars now, but those will be below threshold. So CH Cygni actually was discovered because of the very peculiar photometric behavior, and Y Geminorum because of X-ray emission, but those searches will not find them. So if you will actually start with a sample of spectra, then those will be discovered, because even with a relatively low resolution of 1000, you can see the emission lines. But if you start with the narrow band photometry or BPRP spectroscopy or something like that, you will miss them. So that would be a huge step forward with the large spectroscopic surveys. And also what I think, then that's my last two slides. Galactic symbiotics, yes, but extragalactic symbiotic, that would be a game-changing facility for that. So here is how it looks like in SMC and LMC. In blue, these are confirmed symbiotic stars. In red, these are candidates. So for example, in LMC, you see that there is nothing in this densest region of LMC. But the advantage of extragalactic symbiotic stars is in the fact that you know the distance, so then you can get all the distance related parameters. You can compare with the evolutionary models. You can have a magnitude limited samples, so you can actually understand what you are picking up, because in galaxy, in Milky Way, that's more random selection very often. But the problem with Magellanic Clouds is that these are relatively big on the sky, so then you need to sample a lot of times the galaxies. It was done in M31 and M33 actually, because these are smaller, so it's much easier. But still you see that the number of the systems is not like super huge. One of the reasons is that you are limited by magnitude. But for example, with M33, with the WST, you can have 30,000 candidates with low resolution fibers. And actually the whole galaxy will fit twice, because it's like 1 degree what is shown here, and the WST field is 2. So basically you can sample galaxy like that in one observation. And there are other galaxies that we can still try. So we can have known distances, well understood samples for all the population analysis. And we have stars in that were born in different environments, different chemistry, different metallicities. So we actually can really start understanding how these systems evolve and why. And with that, I will finish, and I will be open for questions. Thank you.
Thank you very much, Jaroslav, for this very super interesting talk. It's now time for questions, comment, and discussion. You can raise your hand or text in the chat. I will start several questions. If you can
I think Alberto.
Oh, sorry.
That's okay. I can.
Do
you hear me?
Okay, yeah.
Yes.
Go.
Okay. I can ask after, no problem.
No. It's okay. Please, you first.
Okay. I wanted to ask two things especially about your introduction. When you said that symbiotic stars are important, you mentioned two things. One is white dwarf magnetism, and the other is close double degenerates. So relating to close double degenerates, I was wondering how you can form very tight white dwarfs from symbiotic stars, because you have a stable mass transfer, and in principle you don't reduce the orbital separation dramatically like in a common envelope phase. So how do you form close double white dwarfs? And then is how you can constrain magnetism on white dwarfs.
So to first question, yeah, the thing is that now you have a red giant donor and a white dwarf, which is accreting. We see that there is a mass transfer, and the orbital periods are of a few hundreds of days. The thing is that the mass transfer is not well understood still. The whole story is that people before thought that this is a wind mass transfer because when people estimated the sizes of the donors from, for example, spectral type, from some calibration or from rotational velocities, they were smaller than the Roche lobes. Then infrared photometry came, and it actually started to look like that a lot of symbiotic stars are filling the Roche lobes, and that should not be stable. By no way, because you have a mass ratio, so the donor is 2-3 times more massive than the accretor, so it should not be stable, but it seems that it is for whatever reason. The thing is that then these are actually two papers from this year where I used the interferometry, and it doesn't seem that they are filling the Roche lobes. So it can be a wind Roche lobe overflow or something. But anyway, the current, if they are filling the Roche lobe, it should not be stable mass transfer. If it is a stable mass transfer, it's stable now. If they are, it's a wind mass transfer, but the star will still grow significantly. The donor will grow. So then it's probably unavoidable that you will end up in a common envelope at some point in the future. Not at this moment, but in the future. And then you can reduce the size significantly. And with the magnetic white dwarf, that's a very nice paper of Diego Belloni, 2024, on one of the symbiotic stars. Because there is a hint of magnetism in a few. It's kind of indirect because it's based on the detection of a periodic signal in blue, which people claim is a rotation of a magnetic white dwarf. So there is a, some stream of material because of the magnetism. So these are typically periods of tens of minutes. But they have a very nice paper where they are showing actually that the symbiotic phase is essential to have the magnetic white dwarf. To have the magnetism in the white dwarf, and then the outcome of the evolution after the symbiotic phase would be double white dwarf, where you will have one magnetic white dwarf. So it's a paper by Belloni, 2024. It's very nice.
Is this the scenario that involves AR-SCO and then the formation of polars in cataclysmic variables, or is this another one?
I think it was kind of similar, but I'm not an expert on that, so I would point you to the paper. But
okay. Thanks anyway. Thanks.
Thank you, Jaroslav. We have another questions from the audience. Please, let's continue with the link.
Thank you. Hi, nice talk. Nice to meet you also. I have two questions if we have a time. The first one, how do you distinguish ULX from symbiotic stars, especially when considering extragalactic studies? And the other one, and I know that there are studies in the literature that use long-term phase-dependent spectral observations of binary stars to separate their components, for example, centangling. What are the challenges in applying these methods to symbiotic stars? Thank you.
So I will start with the second one. The main problem is that in any case, you cannot do any spectral disentangling in symbiotics just because these are SB1 binaries by definition, because you have a very hot white dwarf which is not contributing at all in optical. So you cannot have this nice, SB2 solution with masses or so. So in optical, what you see is the red giant. So from red giant, you actually can then get the radial velocities and you can get the orbital solution. And you see the nebula and the nebular emission. So there were efforts, for example, to use some of the nebular emission lines as tracers of the motion of the hot companion. which is then kind of SB2 solution, but it doesn't seem to work super well. The thing is that as you saw in the ERA query case, the nebula is very complex. So then you need to be sure that actually the line that you are tracing is formed in the super vicinity of the white dwarf and not somewhere in between or behind where it's so this is not ideal. So I don't think that the spectral disentangling and any methods like that will work. The other thing is that the problem with the contaminants is that I think it's actually a bit easier in extragalactic environment than in galactic, just because then you kind of know the luminosity. And you need to do spectroscopy, because without that, it will not work. But with spectroscopy, you can be sure that you have a red giant donor. And then the traditional definition of symbiotic stars is based on the emission lines you see. So you are trying to find hydrogen and helium and emission lines with high ionization potential to be sure that these are not produced, by pulsations or just by, the cool star itself. So typically you try to find the oxygen 3 at least, which is 35 electron volts. So you need something like 35,000 kelvins to produce that. The only problem with extragalactic ones is that typically, given the angular resolution you have, you can have some gas, that is just in the fiber by chance. In superposition on your spectrum. So then what is really helpful are kind of diagnostic diagrams where you have the ratios of fluxes in the emission lines, because they can help you to separate, because the density is influencing that and the electron temperature, and there is a specific range of these parameters for symbiotic stars, so they can help you to separate from other objects.
Thank you so much. Thank you.
Okay, thank you, Jaroslav. I think we can conclude the session here. Thank you again for your talk and sharing your ideas with us. And thanks to all of you for joining and participation in the discussion. We look forward to seeing you at our next talk that will be held by Dr. Sasmita Das on September 23 at 10. Have a great day, everyone, and goodbye. Bye.
Thank you very much. Bye.
Bye-bye.